My name is Dr. Louise Royer, and I have taught the course of Physics 11 based on the Ontario curriculum for many years. In doing so, I had prepared keynote lectures to cover the material for the course. The main topics are kinematics, forces, energy, waves, electricity, and magnetism. The lectures are mostly concerned with the theoretical aspect of the course. However, I want to start with the experimental aspect of physics because it will have an impact on how numbers are viewed and used in the rest of the course. By measurement, I mean the quantification of a physical characteristic using a measuring device. Measuring devices can be classified into two types: digital instruments and analog instruments. A digital device displays a number, such as this multimeter, which is showing the number 1.615. The dial on the instrument indicates that a voltage is being measured, so the number is 1.615 volts. An analog device, on the other hand, does not show a number so easily. The experimenter must compare the level of a liquid or the position of a hand to a calibrated background. A typical clock is an example of an analog measuring device. This particular clock also has dials for the analog measurements of the temperature and the humidity in the room. Let's start with how to measure with a digital instrument, which seems to be the simplest of the two types. Let's say that you want to measure the time it takes for a ball to free fall from a certain height using a digital stopwatch. You know from the manufacturer of the instrument that the number displayed will be in seconds. So the instrument is started when the ball is dropped and stopped when the ball reaches the ground. You see afterwards that the number displayed is 1.37. You might be tempted to say that the measurement of the time it took for the ball to fall is 1.37 seconds. But is it? Let's have a closer look at the number displayed by the instrument. The number does not go beyond the hundredth of a second. This instrument is limited to display only numbers that are multiples of 0.01 second. Another way to say it is that the numbers are increasing by jumps of 0.01 second, by increment of 0.01 second. It means that the instrument is incapable of displaying a falling time of 1.374 seconds, for example. In effect, all the falling times above 1.37 second, but smaller than 1.38 second, will be displayed by this instrument as being 1.37 second. What the instrument is telling you is that it takes at least 1.37 second for the ball to fall. In conclusion, a display of 1.37 means that the time it takes to fall is somewhere between 1.37 second and 1.38 second, but you do not know where it is exactly within that range. The previous exercise reveals an important feature about measurements. When measuring, you are not seeking a single number. Instead, you are trying to establish a range of possible values. The fact that a measurement is a range of values is not reserved to digital measurement of time. All digital instruments have a limited precision since they cannot physically display an infinite number of digits. The number displayed will be an approximation of the true value. So, unless otherwise informed, we will consider the number displayed as being the lower limit of the range of possible values. But information about how far the range may extend must also be provided to completely describe the measurement. A range cannot be described with a single number. It needs two numbers. Those two numbers could be the lower and upper limit of the range, like what was done in the previous exercise. But this is not the most typical way of coding a measurement. A different way to describe a range is to mention the middle value of the range and how far the middle value is from the minimum or the maximum value for the range. The middle value is labeled as T best, and the separation between the middle and the edge as epsilon t. Once these two values are calculated, the measurement is coded in the format T best plus and minus epsilon t. Since T best is the middle of the range, it can be evaluated by finding the average between the minimum and the maximum values of the range. Since the separation between the middle value and the maximum value is the same as the separation between the middle value and the minimum value, epsilon t can be evaluated as the separation between the minimum value and the maximum value divided by 2. Using the minimum and maximum values of the previous example, we get 1.375 for T best, which is the middle of the range. The separation between the middle and the edge of the range is 0.005 seconds. Combining that information, we get a measurement of 1.375 second plus and minus 0.005 second. Please note that you can get back the lower and upper limits by subtracting or adding epsilon t to the T best. But why is it better to code a measurement with the middle of the range and half the width of the range instead of the minimum and maximum values? Remember that the measurement is meant to quantify a physical characteristic. If you had to choose only one number within the range to approximate that characteristic, which one would it be? If you picked the display number, you would be underestimating the true value all the time. Picking the maximum value of the range would mean that the real value is below it all the time. Choosing the middle value gives you as much of a chance for the estimate to be above or below this unknown real value. The middle value is then our best estimate of the quantity. What about the epsilon t? What is its significance? If it was 0, there would not be a range of values. The bigger it is, the wider the range of the possible values, and the less precision we can assign to our best estimate. It is called the measurement error. In summary, making a measurement is not only establishing an approximate value for a quantity, the T best, but it is also quantifying how badly we're quantifying it by estimating a measurement error. I want to add that there are in general more factors influencing the measurement error than the ability of the instrument to display a number, but we will ignore those at this stage and in this course. For the specific case of a digital device, the maximum value of the range is established by adding the smallest increment to the display number. It means that the separation between the maximum and minimum values is the smallest increment, and that the measurement error for that instrument is half of the smallest increment. Let's have a look at another example. If the display number is 4.6 volts on a multimeter, the numbers displayed would be, in general, separated by 0.1 volt, giving a measurement error that is half of the smallest increment, so 0.05 volt. In conclusion, the measurement would be coded as 4.65 volt plus and minus 0.05 volts. It looks as if you get your best estimate by adding the digit 5 to the right of the display number, but be careful about this assumption. It is only true if the last digit of the number displayed by the instrument can use all different digits. We had assumed that it was the case for the preceding example. But a bathroom scale set to display the weight in pounds might only show even last digits, in which case a displayed weight of 145.6 pounds would have a measurement error of 0.1 pound, half of the smallest increment of 0.2 pounds. The same bathroom scale set to measure in kilogram instead might be able to display all 10 possible digits for its final digit and have an error of 0.05 kilogram. Now that you know how to measure with a digital instrument, the next step is to turn to the special challenge of measuring with an analog instrument. This will be the subject of the next installment.